So if we have the carbon, which is effectively electrophilic, we have the oxygen that is nucleophilic, then what we can say is both, we can undergo nucleophilic and electrophilic reactions. Okay, and we're just looking at just the simple stuff to start with. So let's look at nucleophilic first. Okay, so again, it doesn't really matter what's attached to that carbon other than the carbonyl oxygen. And what we're going to say is we have a nucleophile, okay? It's got a formal, we're just going to make it nice and easy, standard nucleophile with a negative charge. Okay, so it's a really strong nucleophile that we're going to use. And we know that the carbon is electron deficient, okay? And so what we would do is we will take the electrons from here and we will react them to create a new bond between the nucleophile and the carbon. Now, if we did nothing else, there would be a problem here because carbon at the moment has got 4 bonds. It's got 3 sigma bonds and a pi bond. It can only have 4 bonds, but by creating a new one between the nucleophile and the carbon, we've created a 5th bond. So something's got to give. It can only have 4. So what do we do? Well, what we know, because you did it with Dr. Allman, is that the energy of a sigma bond is far greater than the pi bond. Okay, the sigma bond is stronger than the pi bond. Therefore, if we're going to break anything, it's going to be the pi bond that breaks first. Okay, so that carbon-oxygen double bond, we are going to take the electrons out of the double bond and give them to the oxygen. Okay, so we're going to take them out of there and give them to the oxygen. Okay, what that will result in is nucleophile, and the oxygen has gained an electron from this process, so we've moved those 2 electrons have moved. One of them already belonged to the oxygen, one of them didn't, so it's gained an electron, so it gets a negative charge. Okay, so we've added the nucleophile, so you can see how that's a nucleophilic addition. What about electrophilic addition? Because we've said that we can do both. So how do we do an electrophilic addition? Well, we need our electrophile. Okay, so we have our electrophile here. We have an oxygen atom which has got some nucleophilic character. We did that on the first slide where we said the oxygen is the one that has more electron density, it's delta negative. So therefore, the oxygen is the one that would do the reaction with the electrophile. So we would use a lone pair of electrons from the oxygen to form this new bond. So what that will give us our electrophile will add, and we have a positive charge on our oxygen. But we know oxygen is really electronegative. Okay, it's really not going to be happy to have a positive charge, especially when it's attached to a carbon and the oxygen has more of a pull over the electrons than the carbon. So it can say, well, you know, carbon's fine if it doesn't have some electrons, it can cope a little bit better than me, but I really, really need the electrons. So we can again show that what this really means is a resonance structure in which the electrons from this double bond can be donated to the oxygen, which gets rid of that positive charge. And so the carbon can be considered to have the positive charge on it in this. Okay, so we're going to use that later on. So we're going to use the ability that a strong nucleophile can react with a carbonyl group, as in the top one, and equally that the carbonyl group can react with an electrophile. And what that actually does is it makes the carbon more electron deficient. because we can draw that resonance structure which shows the positive charge sitting on the carbon. And in this case, if we think of that as an equilibrium, it's more likely to sit like this with the positive charge on the carbon, because that's a more stable situation. The oxygen, being electronegative, really doesn't like to have given off its electrons, so if it can get them back, it will do. So we can consider the carbon in this end bit with the electrophile attached is more electron deficient. Okay, so that's the kind of fundamentals. That is the key. If you can get that into your mind, that will help you to understand all of the reaction mechanisms we're going to look at, because they effectively come from this. They come from showing that the carbon will be attacked by a nucleophile, but if you have something there which the oxygen can react with, it actually makes the carbon more susceptible to nucleophilic attack. Okay, so if we're going to do a reaction, if we're going to add something to a carbonyl, we actually usually involve both of those steps, both a nucleophilic part and an electrophilic part. And the order in which we do them just depends on the conditions that we put into the system. Okay, so if we started with some basic conditions, okay, under basic conditions we would have our carbonyl group, okay, and under basic conditions we're going to have a strong nucleophile, okay. We'll still use Nu minus, but imagine, what's the classic base that you would know about? You'd think hopefully sodium hydroxide. Yeah, sodium hydroxide is a classic base. So sodium hydroxide, NaOH, actually gives you OH minus. Okay, so when you're thinking of this, you know, I'm just using a general nucleophile because I want you to understand it doesn't matter what the nucleophile is, but if it helps you, think of the nucleophile as something like OH minus. Think about it being a really strong, negatively charged species. Okay, so what would happen is exactly the same that we've done before. The nucleophile is going to attack the thing that is electron deficient, that is the carbon. Carbon would then have too many bonds, so we need to break a bond. So we are going to break the carbon-oxygen double bond. You're going to get really sick of me saying that by the end of this series of lectures, because I will say it every time. And if I don't, please remind me, because it's so important. No matter how many times I say it, unfortunately, it will be the ones that aren't here to hear it. Come the exam, there'll be someone that will break a single bond before they break that double bond, and then they'll be wrong, and I'll get a little bit sad. So always break the carbon-oxygen double bond, please. Okay, so, oops, cancel that, please. Hang on a second, let's go back. Right, so we've done that double bond, and it's changed the colour again. Why does it keep doing that to me? Right. So what that gives us then is we've got our nucleophile that's now bonded to our carbon, and we've broken the carbon-oxygen double bond, so we have an oxygen with a negative charge. So that is exactly the same as we saw a slide ago. Okay, nothing different, exactly the same. But what we're now going to do is say, well, we've got this under basic conditions. What that means is quite often, if we're using something like sodium hydroxide, we'll have it as a solution of water, so there'll be water around. So if you then put in water as H2O, and I've drawn it specifically showing, you know, a bond between the oxygen and one of those hydrogens, because we can then say, well, actually, under these conditions, that hydrogen is slightly electrophilic. Okay, we know that in water we have this dipole as well. We have a delta negative oxygen and delta positive hydrogens. If you don't know that, I suggest go back and look at whatever you did before, because that's something which clearly should have been taught. It should be in your A level, it should be in your BTEC, it should be in whatever you've done before this. The idea that water has a dipole to it. So we can then take the electrons from the oxygen, pick up the hydrogen, which is effectively a proton. And what this gives us at the end is we have our nucleophile, and we end up with adding a hydroxyl group to it. And most importantly, we would regenerate OH minus. So if we were using that as our nucleophile, we will have regenerated it. Okay. So what you can see there is, depending on the conditions, the basic thing says nucleophilic attack happens first. So nucleophilic attack, and then once you've done the nucleophilic attack, then you have the electrophilic attack. So we put both things in the same reaction mechanism. So that's happens under basic conditions. So when you're looking at these things, look for what else have I got in my reaction mixture. If I see a carbonyl, do I have an obvious base? And in a minute we're going to look at acids, so do I have an acid? Okay. So that's the basic conditions. We've then got acidic conditions. Okay. So under acidic conditions, we're going to do the opposite. We're going to do the electrophilic first and then the nucleophilic. So under acidic conditions, we're going to have H plus in there. Yeah, that's what an acid is. It gives a source of H plus. H plus is an electrophile. Therefore, our oxygen in our carbonyl bond is going to react with the electrophile. So the lone pair of electrons here going to form a new bond. Okay, and so what we've done is we've protonated, we've added a proton to our carbonyl group. Okay, and as we said before, the key thing here is that this ultimately means that the carbon is really now electron deficient, because the oxygen in this middle bit, when it's got the positive charge, is going to pull the electrons away from the carbon. So what we've effectively done by adding the proton is we have activated our carbonyl group. We've made it far more reactive than it was to start with. And if we're not using a very strong nucleophile, that's what we need to do. So now, if we look at we can use a nucleophile that isn't charged. I'm drawing the hydrogen on there for a reason that you'll see in a minute, okay? But there's no charge this time. It's just a weaker nucleophile that happens to have a lone pair of electrons. Okay, so we've got our activated carbonyl group. So now we don't have that formal negative charge. We don't have a strong nucleophile. We have a slightly weaker one. But because the carbon is so much more electron deficient, it's going to get an electron from somewhere. And so it's going to take it from this uncharged nucleophile. And again, that nucleophile is going to add to the carbon. The carbon would have 5 bonds. So therefore, we need to break a bond, and we're going to break the carbon-oxygen double bond. So that will end up, we will have our nucleophile attached to our carbon. We've neutralized the positive charge that was on the oxygen, but what it means, because the nucleophile has given its electrons away, again, it had so control of 2 of them, it's given them both away to create this new bond. So effectively it still retains one in that bond, so it's given the other one to the carbon, therefore it gets a positive charge. And then at this point, we've got that hydrogen that handily is there, and what we can do is we can lose the proton. Okay, and if you're going to now ask, how do we lose the proton? Okay, the answer that's going to come back is, we don't know. There are so many ways it could happen, we don't need to show them. Again, you're doing this under acidic conditions. So already you've got some acid in there. Let's say it's HCl, okay? The proton that you've used at the top here came from HCl, so the Cl minus is still floating around in solution. So a Cl minus could come along and take that proton. But again, if you're doing it under things like HCl, you don't do it in neat HCl, there might be some water in there. So a water molecule might come along and take that proton. Equally, the very first thing we did is protonate our oxygen. Now, that oxygen could get its proton from the nucleophile here. So there are so many ways in which that proton can leave that molecule. We don't actually have to show it. We just have to know it can happen. And therefore, we can just show the electrons in that hydrogen to the nucleophile bond, going back to the nucleophile, neutralizing the positive charge, and releasing a proton. So, you've got the basic versus the acidic. Question?
The two structures on the top right, are they resonance structures in equilibrium?
Yes, so these ones up here.
Yeah.
Yeah, that's just showing it as a resonance structure. So, if we put this double-headed arrow, that means resonance. Okay, if we're talking about an equilibrium, which usually is more about two species, this is saying about electrons moving within the same species. We would normally, an equilibrium would look like that. Yeah, but in this case, it's not. It's a resonance. Okay, so what does this all mean? Well, it means we can have a general idea of what's going to happen. So most of the reactions, and I will say all of the reactions that I'm going to show you, are going to involve one of two things. Either we're going to have a charged nucleophile, so something which is a very strong nucleophile that is going to react with an uncharged carbonyl. That was that basic conditions. That was the first one we showed you, where the nucleophile is attacking the carbon. So that's your nucleophilic attack. Okay. The other one is that we're looking at the attack of a lone pair of electrons of an uncharged nucleophile to a charged and activated carbonyl. Okay, so the first one, just to recap once more, just to show this is what you need to think about. Okay, so a charged nucleophile and an uncharged carbonyl, these will react to add your nucleophile. Okay, so that's the first one. And then the second one would be, we would be taking a we're going to take a charged and activated carbonyl, okay, and we're going to react that with an uncharged nucleophile. Okay, so that is what you need to remember, and what you'll see is at the start of every lecture we're going to come back to this slide. Okay, we're going to remember this because this is the fundamentals. This is the reaction mechanism that happens all the time. And what you can see is the arrow movement is the same, isn't it? Okay, look, at the start, the two arrows show something coming from the nucleophile to the carbon of the carbonyl. The carbon-oxygen double bond breaking. Okay, that is the fundamental reaction mechanism of attacking the carbonyl group. What you just now have to think about is, first of all, how do we make this charged activated carbonyl? So I've shown you that you can protonate. There are some other examples in a minute that we'll look at. And then equally at the end of it, we need to look at, once we end up with our negative charge, how do we finish that bit off? How do we turn that back into something which doesn't have a charge? Yeah? But those are the additional bits. The fundamental is this attack of the carbonyl carbon, breaking of the carbon-oxygen bond, and then there are various routes that we take following that. But get that straight in your mind and that will really help you.